Any questions about the project or things that you're like, it took me a long time to figure this out, and I finally did, and this might be helpful to other people, or a question or something? Yeah.
I know a couple interesting things about the language now.
About the, like, the HDL language? Like what?
If you want to give it a 1 or a 0, you can give it true or false.
Okay, right. So that's, did y'all hear that? So if and I know for sure that's going to be useful, that may be useful in the ALU, may be useful for the memory. For sure you're going to need it when you get to like project 5. If you want to put like a constant value on some wire, instead of having it come from an input, you can say, equals true or equals false. And you can do that even for, if you have like a 16-bit bus, you can just say true, and it's just like all ones, little thing. So that can be useful. So, where you going? Zach?
Yes.
Yeah.
So I was just saying, definitely that was really useful for me for the incrementer at the up in the
For the incrementer. Okay.
in
Yeah.
the appendix that they gave us. But
That's right.
the other thing was it took me a while to figure out that you can't like make the decision about which operation to do before you do the operations. You have to like do
Right.
them all in parallel and then decide.
Yes. Yeah, that's good. You know what? That took me a while to figure out too when I was doing the projects. Because if you're choosing between two things, I really wanted to say, okay, first let's like choose which thing we're gonna do, like have the wires go there and then do it, and then but it's like actually you just do both, and then you just choose which output you want to use. That's all you need to do, because there's really when you're making a circuit, there's no cost to just like doing both things, because they literally happen at the same time, like as the signals are flowing. So you can just split the signal. You can, like, for example, on the ALU, just like add and do and add both, right? And then just decide which of those results you want to use using like a mux. Okay, so you're definitely going to use, if you haven't figured this out already, you're definitely going to be using lots of muxes in your ALU, because that's like how you make all these choices, right? But you don't have to think about it in terms of, I think as Zach was saying, you don't have to think about it in terms of making the choice up front. You do all the things, and then you choose which result you want at the end. I think that for when I started doing the project, I had this complicated thing where like I had a demux at the beginning and then like a mux at the end, and it kind of like split, and then I realized like I don't need that. Good. Anything else? Yeah, Daniel, you have something else?
Not specifying an input pin will not give you an error. It will set that value to false.
Okay. So if you don't specify an input pin, right, it'll just be false. Yeah. Indeed. Yeah. Simon.
A lot of this information is found in Appendix 2 in the textbook.
Okay.
I found that, and it had all the information I needed.
Cool. Okay, so check out Appendix 2 in your textbook if you haven't already. Sounds good. And in general, as you're probably discovering, like, I'm not gonna, this is on purpose, because it would take too long. I'm not gonna give you every single piece of information you might need for the projects in lecture. There's just too many little details that you could possibly need, and it would take too much time. So I'm definitely expecting you to do stuff like that, like go look up in the appendix, or look at the materials on the website, figure things out, and help each other. Like, so that's why we're sharing right now. So. Anything else? Yeah, Zach.
The last thing I noticed was just like troubleshooting in HDL was harder for me because it doesn't give you like a stack trace or anything. It just gives
Right.
you program failed.
Right.
And you have to just figure out why.
Yeah. It is possible to, like, if you have stuff loaded in the hardware simulator, you can like, do things step by step and kind of like look, and it'll tell you like what are the different values on the different internal pins and stuff. So you can kind of use that to do a little bit of debugging if you're like, okay, well, what is actually going on? But yeah, it is harder for sure. But as you can imagine, one of the reasons that people use like hardware description languages in real life is that, I mean, if you just like build a circuit and it doesn't do what you want, like, yeah, debugging that is not fun. So if you have it just in some hardware description language, you could simulate it, you could use tools to help you debug it before you actually print it in silicon, which is helpful. So yeah, the language that we are using is something that the authors of the book made up. So it's not like a real language, but there are real hardware description languages that people use for making hardware. And they work similarly, they're just like way more complicated. So, yep. Alrighty. So I wanted to take some time first to talk a little bit more about the ALU and think through how it does various operations. So I think last time we talked about how we would do. So obviously we can add and we can do and. We also talked about how we would do or by like inverting the inputs, doing and then inverting the output. That gives us or. And I think we talked about how to do not. But there's a lot of other things you can do, and I wanted to talk about some of those. Not because you need it for the project, but because it's interesting. And it's interesting how this ALU is designed to be able to do all these different operations with sort of minimal. All right, so remember that we have. Let's see. All right. I'm gonna do this. Try this. All right. So our ALU, we've got. Remember, we have our inputs are nx. No, let's do zx first because that's the thing that happens first, right? So zx, nx, zy, ny, f, and no. So remember these. So zx is do we turn x into all zeros? Right. Nx is do we negate x or do we invert it or not? Similarly for y, and then f tells us I think 0 is and 1 is add, I believe. Does anyone know offhand if that's correct? That sounds good. Okay. And then no is do we invert the output, after operation is done. Okay. So I want to think through. We can make a little table, and then here's like the operation. I want to make a little table of some of the different combinations of inputs that we could give, and the ones that correspond to some nice operation that we can describe. I mean, because of course, there's 64 possible combinations of inputs, and they all do something, but some of them might not do anything that's particularly useful to us. But, okay, so we already talked about obviously if we just if all of them are 0, right, that just does and. I'll say x and y. If all of them are 0 except f is 1, right, that's just adding, that's x plus y. And then we also talked about if we negate x and y, and we do and then we negate the output, that gives us or. And I think we ended by talking about how to do not. And there were actually a couple different ways we could do it, but maybe the simplest is to do, we invert x, and then we just 0 out y, and then we add them. Right, so that would give us, does that sound right? Yeah, so if we invert x, but then we make y all zeros and we add them together, so that doesn't change the inverted x at all. All right. Okay, so let's talk about some other ones. So I want to, over here, let me remind you that the way negatives work, right, with 2's complement, is to get the negative of x, we invert x, and then we add 1. Right, so for example, if we have, 2, 0, 0, 0, 1, 0, if we invert it, we get 1, 1, 1, 1, 0, 1, and then we add 1, we get 1, 1, 1, 1, 1, 1, 1, 0. And that's the representation of negative 2. And we can also rearrange this equation if we solve for the inverse of x. So we get x inverse is negative x minus 1. Right, so that's going to be useful too. Because our goal is we want to derive some ways to do things with negatives like subtraction or negation. And to kind of show that they work, we're going to need to keep these in mind. Right? So let's start with, how could we do x minus 1? So if I just want to say whatever, I'm going to ignore y, and I want to take whatever x is and subtract 1 from it. Any ideas how we might do that? Or can we make the ALU do that? Zach?
Could we 0 y and then not y, and then add?
Okay, so you're saying you want to do 0 y and not y. So what is that? If we do 0 y and then not y, what do we get?
1
We
y.
get all ones, right? And all ones, if you recall, that is the representation of negative 1. Okay? Because remember, it's like if you're counting down and you get to 0 and you keep going, down 1 more, the whole thing rolls over around to all ones, right? But that's one way to remember it. So yeah, and we saw that addition works just fine on these representations of negative numbers. So if we say add, and then we don't do anything to x, right? We leave that alone, and we don't do anything to the output. Yeah, that gives us x minus 1. And we could similarly do y minus 1 if we wanted by just, leaving y alone and then turning x into negative 1. So I'll just put that over here, or y minus 1. Yeah, I don't mean this also does y minus 1. I just mean we could do y minus 1 similarly. I'm not going to write it all out. Okay. Okay. Let's see. Here's an easy one. What if we just want to get the number 0 out? So this sounds ridiculous, like why would you need that? However, think about like when a computer starts up, like how do you know what's in the memory? Or what's in any particular place? Like it could just be random bits. So it's nice to actually have a way to specifically say, I want to create the number 0 so that I can store it somewhere and be sure that I've got 0 there now. That's actually something you need to do. So how would you just get the number 0 out?
0 them both out.
Okay, yeah, so just 0 them both and then like add or, well, and, it doesn't really matter, right? So you 0 this, you 0 that. We'll do and. Okay. How would we get negative 1 out?
0x, 0 y negate y, and then add them.
Okay, so you're saying 0x, so x is now 0, and then 0 and negate y, so it's now negative 1, all ones. And then add. Yeah, that works. How would we get positive 1? This is tricky. But it is possible.
Zero minus one. Zero minus negative one.
0 minus negative 1, but how do I do,
We
how
make
do I do minus? Like, I don't have a minus operation. I can do a minus on like two things that are coming in, but I can't. Well, no, we don't, no, we don't. We don't have that yet, right? We will, but that, I don't think that will. Garrett?
Would you just take the last one that we did and make the outcome, the output?
Say that again? Do,
Just take
do this,
one,
and then,
negate it.
so, very good idea. So you're saying, look, we can make minus 1, and then let's negate the output. Okay? However, right, this is negation in the sense of flipping all the bits, not in the sense of like taking the negative of the number. Okay, so, right, this will generate the binary string that's all ones. If we negate it, like that is set this bit, it'll just flip all the bits and we'll get 0. Okay, so good idea, but that doesn't actually work. And I'm really annoyed actually that your book uses the letter N for this because it confuses, like, are we talking about negation, like negating a number, or flipping the bits? People use the word negate for both things, but I'm going to try to be careful to use invert for flipping the bits and negate for negating a number. Cookie.
0 and then negate both variables and then add and invert.
Okay, so you want to zero and invert both inputs, so they're both -1. Then add, that gives us -2, which is 1, 1, 1, 1, 1, 1, 1, 0. And then invert that. Yeah, I think that works. And I'll in a second after I write it, I'll tell you another way to think about it. So if we 0 and invert that, 0 invert, and then I add, and then if you actually set them with all ones, that gives us 1. Well, obviously, I mean, if you want a 1, you just like say, no, I really, really want 1. You just like have to tell it over and over 6 times. It's like, okay, I get it, you want a 1. Cool. No, I was going to say, thinking about this, right? If we have -2, and then we invert it, okay, this tells us what we get. I get the negative of -2, which is 2, minus 1, 1. Okay, so you don't even have to know what the bit string is that corresponds to -2, although it could be helpful, but if you just think about this, right, that'll tell you what you get when you invert. Right, when you invert, you always get you flip it from negative to positive, and you always get something that's either one more or one less, and I can never remember which, and you just have to like look at the, but it always like shifts it by 1 in addition to flipping the sign. Okay. So of course we could get -2 as well, but that's not as useful, so I'm not going to write that down. Let's see, what else? What do you want to do? Garrett?
This is just a question. Since
Yeah.
there are multiple ways to get the same answer in some cases, is there like a preference for certain ways for like fewer bits, or is there some sort of optimization, or is that not a thing when it comes to ALUs?
I mean, with this ALU, I don't think it's a thing, because basically, like, in the ALU, right, all the things are happening all the time, and it's just like we're using some muxes to choose, the result that we want. So there's no sense in which, some of these will take longer than others. They all take exactly the same amount of time, and so it doesn't really matter. Now, certainly, when you get to like more complicated, the computers that we have, I don't know all the details, but there certainly can be operations that take more than one clock cycle. We'll talk about what clock cycle means in a minute, but so in that case, there can be differences, because if you can, for example, here's a good example. division, right? So your computer has hardware to do division, but it takes relatively a long time. Division is expensive. And so in particular, like if you were going to divide by 2, you'd rather not use the general division circuit to do division by 2, because dividing by 2 is just shifting the bits over, right? And so it also has a way to shift bits, but that takes just like really fast. And so in that case, that would be something like a compiler would do. It would notice, oh, you're dividing by 2 here, I'm going to output the instruction that tells it to shift bits, not the division instruction, right? So that can make a big difference, but for this ALU that we're talking about, there's no difference at all. It's just, if you can find a way to do it, that's fine. And let me step back a minute and also say, related to that, you know, why are we doing it? Why is it designed this way? And it's really cool why it's designed this way. Because like you could imagine, right, that your ALU has a big list of operations it can do, you know, and some kind of codes that code for each one, and basically you have like a big if, like a whole bunch of muxes that basically like say, well, I'm going to do all these operations, and then just like based on what bits you gave me for your code, I'm going to like see, okay, is it this one, is it this one, is it this one, is it this one? I'm going to like choose the right output, okay? But that's not how this works, right? The code, it's not like looking it up in a table or something. It's just like each of those bits goes to one place and chooses, you know, like tells something what to do. And so literally, you know, if you have some instruction, there's going to be 6 bits in that instruction that it's just going to like yank out and just like send it straight to the ALU, and the ALU will just do what those bits mean to do. So it's a very efficient way to code for all these different kinds of operations without having to have a whole bunch of ifs or like a big table or something like that. Of course, when I say ifs, I mean like muxes. There are muxes, but they're not like the whole mess of them you would need to like choose on a big list of possibilities. All right, let's see. What operation should we do next? We could do like, let's just do negation. So what if I want to do like negative x? Like flashing binary symbols to me. Simon?
You could 0 and negate y, and then add.
And then add.
Yes.
And then just do nothing with x,
Yeah, nothing with that.
and don't invert the output. Okay. Let's see. I don't know how my rows are getting off here. So okay, if we 0 and negate y, that'll turn y into -1, and then we're going to add. So that actually gives us x minus 1, right? Because we're taking x unchanged, and then this gives us -1, and then we're going to add. So that is a useful thing. Oh no, we already did that, didn't we? Oh, we already have that. Okay, yeah, so we've already done that. That doesn't give us -x. Yeah.
Leave x alone, 0 y, add y, negate the output, or invert the output.
Like that?
Yeah.
Okay, let's see. So you're saying, so we have x unchanged, we're going to 0 y, and then add. So this gives us, oh, so it's x plus 0. It's just x. It's just, isn't that just the inverse of x?
Yes. Yes, it
Zach?
Do we need to, so what if we negate x, then negate, or then 0y, and negate y, then add it, and then flip the output? Am I?
Okay,
am I way off?
well, that maybe seems promising, like we're doing multiple, like, negating things. So, okay, so we invert x, and then, okay, we zero and invert y, so that'll give us -1, right? We add, so x plus -1, that is like, and then we invert the output, so it's like this, right? So what is this? Well, we can just apply this. So this is equal to negative x inverse -1 minus 1. Right, I'm just applying this equation here. I can apply this equation a second time to say this is equal to negative x minus 1 minus 1 minus 1. Am I doing this right? Which is x plus 1? Right, this is x plus 2 inside here, but when I negate it, then minus 1. Well, that's a useful thing. It's not negative, but no, but we want that. Like, incrementing something is a very useful thing, so, okay, we'll just, cool. I mean, it's part of the thing here is you can just try random stuff and just see what you get, and it's like, maybe it'll be useful. Is this right? I'm like second guessing this. Did I do something wrong? No. So, all right. Anything else you want to try? Yeah, Claudia.
So the same as the last column, but don't negate either x or y, but still negate the final position.
So you want to say,
I think we're close, I just think we negated.
okay, so what do you want to do? You want to 0 y?
0 y, don't negate y,
Okay.
and then add, and negate operation.
And negate the output. So this is going to give us like here,
No,
x plus 0 inverse. That's just x inverse. It's the same as this row, except in this case we inverted x first and then didn't invert the output, but here we invert the output, but it's kind of ends up being the same thing. You might think we're running out of possibilities, but there's 64 combinations, so could we?
I guess we could try zeroing y, negating y, adding, and then negating the final. That would be x.
Oh, okay, but don't do anything to x. Is that what you mean, like this?
Yeah.
Yeah, okay, let's try that. That seems promising. Where's this? So this is x minus 1 right? This is -1, we're adding, and then we just negate that. So what does that give us? Whoa.
A scroll.
Right. So that is, I'm touching the, that's what, I got it. Negative x minus 1, right? And that is negative x plus 1 minus 1. The ones cancel. Negative x. Cool. Yeah, that gives us negative. All right. Let's do one more. Because we really, the other thing we really want is to be able to do like x minus y. Right? If we can't do subtraction with our ALU, it seems like, I mean, of course, we could always, since we can do negative, right, we could do it in 2 steps by first computing negative x and storing that somewhere, and then adding that to y. But that seems dumb. Like, hopefully we can do it in one step. So any ideas how we can do x minus y? And maybe using some of the insight that we got from these previous ones. Any ideas? Zoe?
Could you negate y and then add?
Negate y. Don't do anything to x. And then add them. So, and then negate the output or not? No. So that would give us, I mean, that would be x plus y inverse, right? But y inverse is not quite the same thing as negative y. So that's going to be like, it's going to be x minus y minus 1. Right, so it's very close. Zach?
What if we tried negating x and then don't do anything to y and then add and then flip the output?
Okay, so you want to, instead of negating y, you want to negate x, but then negate the output also.
Yes.
Okay, let's try that. So, right, so maybe your intuition here is like, well, we need to like negate twice to like get rid of this like extra 1, but if we want to end up with y negative, then we need to negate x first, or invert x first, and then invert it back. So let's see, that would be inverse of x plus y inverse, right? Actually, like this looks very similar to this, right? In this case, like we started with -1 and we ended up with +1. So here, if we start with plus y, we will end up with minus y, right? So I'm just going to say equals x minus y. You can work through the details if you want. It's just applying this equation again. But yeah, it turns out that actually does work. And we can do y minus x, of course, by doing it the other way around, which might be useful to have both. Okay. That, I think we hit most of the important things. So we can now negate, we can subtract, we can add or subtract 1. We can get constants like 0, 1, -1. We can do and or not. That's pretty good, right? That's a pretty good kind of list of fundamental operations that we can instruct the ALU to do. You know, just using these basic building blocks of, you know, the AND gate and the addition circuit that you guys are building, plus the ability to selectively invert and zero stuff out. And all that combined gives us a lot of flexibility. So, yeah, nice. Any questions?
I'm guessing we can't multiply.
We cannot multiply. No, so this is a good point. So of course, any modern computer has hardware to multiply. Okay, but multiplication circuits are a lot more complicated than addition circuits, and we're not going to talk about them in this class. Partly because for time, and partly because I don't understand how they work. I mean, I'm sure I could learn, and you could too, but, and your book doesn't talk about them. So, and that's a deliberate choice that your book made to say, all right, we're just hitting the fundamentals to be able to build a working computer. So, we are going to be able to do multiplication, but it's going to be implemented in software instead of in hardware, right? So when you want to multiply, basically, we have to write a little loop that like does some additions, okay? And we're gonna get to that. We're gonna do that. So ultimately, the operating system that we're gonna build will provide a multiplication operation. So you can write programs that just say multiply, but then that'll get translated into code that actually has a loop that calls a bunch of addition operations. And it'll be more efficient. It won't just like, say, oh, you want to multiply 25 times 397? Okay, fine. Add 25 397 times. No, it's going to be more efficient than that. It's going to use binary and stuff. But it is going to be in software. And generally that's a real trade-off that that hardware designers make is like, well, we have to draw the line somewhere between what does the hardware provide, and then what would you have to build on top of that, by just calling instructions that it provides. Certainly, most modern PCs and stuff go very much towards the end of let's provide as much stuff as we can in hardware to make them as fast as possible. But you can imagine like other things like, let's say you want some kind of embedded device and you want it to use very low power and be very easy to cheap to fabricate. Maybe you want to make the hardware really simple and just say we're just going to provide these bare bones operations and you can build whatever you want on top of that in software. So, all right, cool. Any other questions? All right, good. About like half an hour. So let's start talking about memory. So at this point, right, so we can do math, we have things like muxes and demuxes that can do kind of if-like operations. So at this point, we could build, given this, we could build something that would basically like, do a bunch of math in a sequence, and maybe with some ifs in there. But what we can't really do is have any kind of loop, okay? Because if you're going to write a loop, that presupposes that you have some kind of memory so that you're remembering like how many times has the loop gone, or maybe there's something that is, you're like, while this is true. But when you say while something is true, that presupposes that it's something that's going to change. Like it starts out being false, or it starts out being true and eventually becomes false. In order to make that work, you need to have some way of remembering some information. And so, and obviously, right, you know that computers have memory. But that's really the only other thing that's missing. So once we build some memory, we're going to be able to put that together with the ALU and a few other things, and like put that all together into a working computer. So the question is, well, how does memory work? So your book actually takes as given a thing they call a D flip-flop, and it just says, don't worry about how this works. Here's what it does, and then we're going to use that to build memory. But because it's cool, I'm actually going to show you, like again, starting all the way from NAND gates, like how would we actually build, some working memory circuits? Because it turns out that you can just build memory out of logic gates, just like we can build other things. There are other kinds of technologies. There's lots of ways you could make something that remembers things, but it is possible just to build it out of logic gates. And in fact, like the RAM on your computer literally is built out of logic gates. Something like a USB drive, like flash ROM, that's not. That's like a different technology. But the RAM in your computer probably is literally built out of logic gates. So let's see how it works. So we're gonna build something first called an SR latch. And conceptually, it's got two inputs, S and R, and it's got, usually this is called Q, I don't know why. These are like traditional letters when you do these things. I'm gonna call this Q out. Okay, and then how do we talk about it being memory? So it's not just, we can't just talk about it literally like in terms of these inputs map to this output. Because we want the output to kind of like remember what it was before. Okay, so how do we do that? When we have a circuit, we literally have the output loop back as an input. So, all right, we're gonna call this Q in. Okay, so Q in is like whatever value the output was last time. I'm waving my hands a little bit, and we'll get more into that in a second. But basically, like Q in is like what the output is currently, and then it's going to use that to figure out what it wants to do next. And you'll see this is literally how we're going to build. Like this is the trick. This is the one trick that lets us build memory out of logic gates, is that we can have circuits that loop back, so their outputs go back as inputs. Okay. So here it is. So what does this mean? S stands for set, and R stands for reset. So set basically means, hey, we want to set this to 1, and then it's going to remember 1 from then on, until, like when we do R, it's going to reset it back to 0. So S, R, Q, N. Well, no, you know what? I'm just going to say. So this is a kind of pseudo-truth table. You'll see why I say pseudo in a second. But when S and R are both 0, it means we don't want to do anything right now. It should just remember the value it previously had. So under Q out, I'm going to write Q in. So this is why it's like a pseudo-truth table. I'm just saying like Q out should just remain the same value, whatever Q in currently is. It'll just keep the same value. Okay, when S goes to 1, then we want Q out to be 1, because we're setting it. We're saying, hey, I want you to be 1 now, and from then on it's going to be 1. If R is 1, then it's going to become 0, and if they're both 1, sad face. Okay, don't do that. Now, in practice, it depends on how you build it. Some ways of building an SR latch, like this is really bad and it'll like make things blow up, or like just not actually literally blow up, but like maybe oscillate, between values or do weird things. Some other ways you could build it, which actually the way I'm going to show you, it turns out this works fine and it acts just like a reset. But the point is, like conceptually, this is not a thing that you're supposed to do. You should, you can signal that you want to set it by putting the S to high, or you can signal that you want to reset it by putting R, but you don't do both at once. That doesn't make sense. Okay, so how are we going to build this? Well, yeah, I remember how it works. I'm just trying to remember like how I would explain it, but I'll just draw it. Again, this is just for fun. So this is an OR gate, and the idea is this is my Q. This is my set. Here's my reset. So. And here. Here's Q out. Oops. I'm just gonna draw it and then we're gonna talk through so I convince you that it works. Okay, this is Qn, of course. So how does this work? Oh, this is a not gate, by the way. I don't remember if I talked about that. So let's just go through these different rows of the table and see if we can convince ourselves that it behaves like we want it to. Okay. So let's say that S and R are both 0. Okay. So when R is 0, this is a not, so it turns into a 1 here. And so now we have a 1 going into this AND. Okay. S is 0, so that won't make the OR be true. So if Qn is 0, then a 0 is going to, like, basically setting this to 0, right? 0 false is the identity for OR. So it basically just means like this is acting like a wire. Like whatever value this is going to go through. If this is 0, then the OR is going to be 0. If this is 1, the OR is going to be 1. So whatever Qn is, it's just going to go right through to here. And then, well, this is 1, and that's the identity for AND. So in that case, like basically, it's almost like these gates aren't there. They're just letting through whatever the signal is straight to there. So it's just like a loop that's going around, right? Whatever Q out currently is, it's going to go through here. It's going to go right through and right through Q out. Okay, so that works, right? Whatever Q out is, it's going to stay that way. What happens when I put a 1 here on S? Well, that means that for sure, this OR is going to output a 1. It doesn't matter what Qn was, right? Because anything OR 1 is 1. R is 0, right? So not 0 is a 1. So there's a 1 coming here. There's a 1 coming in here. That means definitely a 1 goes out there. And now we've just set Q out to 1. Okay? And vice versa, if R is 1, right, this is a 1 coming in here, so a 0 goes up here, which means anything and 0 is 0, so a 0 goes out. Okay? So that works. And probably you could like look at this truth table and work out some things and kind of like derive this, but I don't remember how to do that. And I didn't feel like doing it on the fly. So if you want to think about it later, I'm going to draw one other way that you can make an SR latch, just because it looks cool, and I'll let you think about why it works. So, let's see. So this is a NOR gate. So it's like an OR, but then it inverts, it negates the output. Okay, the little circle means to negate. And I think this is Q out. I could be mistaken. It could be that this one is Q out, but I don't know. It's one of them. I'm not going to talk through this one, but it's fun to like stare at it yourself and see if you can convince yourself that this works in the same way. But it's just like two NOR gates that are both feeding back into the other one. It works. I think, so like this one is conceptually much easier to understand why it works. This one I think is like easier or cheaper to actually fabricate. Because I think like NOR gates are very cheap. You can make like with 1 or 2 transistors or something. And the fact that you just have 2 NOR gates connected like that. So I think in practice, SR latches are maybe built more like this, not like this, but this is conceptually better. But don't quote me on that because I don't actually. All right. Any questions on what an SR latch is supposed to do? How it works? Okay, so an SR latch is great, and we're going to use that as a building block, but it's not very satisfactory yet as a memory, because, well, let me show you something else that we're going to build, and you'll see why I think it's going to be more useful. So, make something else called this is called a D latch, or a data latch. Okay, and instead of having set and reset inputs, it's going to have an input called data and an input called set. And then it's going to have Q out. And the idea is, well, let me draw you the truth table for it. So data, set, Q out. And of course it has a, think about Q in. Maybe my pen just ran out of batteries. All right. Turn this on. So the idea here is that instead of having set and reset, where set means, okay, I want to remember a 1, and reset means I want to remember 0, data is going to be whatever we want to remember. And then set is going to say whether it should remember something new or not. So if set is 0, then it ignores data, and it just keeps remembering whatever it previously had. If set becomes 1, then whatever value is on data right now, it's going to remember that new value. Okay. So, right, SR latch is about, do I want to remember 0, do I want to remember 1? A data latch is, do I want to remember something right now or not? Or should we ignore? So, in particular, if set is 0, then Q out is Q in. If set is 1, I mean, really I should just say, I don't even have to write this, right? That's the idea. If set is 1, then Q out becomes whatever data currently is. And this is, you can imagine, this is more useful because, how are we going to use this? Like maybe our ALU, there will be some value coming out of our ALU, right? Like it just computed some value. And, that's going to get sent to the memory. And then we, maybe there's something where we're going to decide, do I want to store that value right now or not? Right? And then we would like set something to 1, meaning, yeah, let that value in, store it in the memory, remember it. Or if it's not 1, then it just means, yeah, it was computing a value, but we don't care about it. Just forget it. Because like the ALU is always computing values all the time. You can't stop it from computing values. But you can decide when you want to, think about like the data is like this stream that's flowing by constantly. And it's just like you've got the set line is like a little gate that you can lift up to let some water in, when you want it, right? So how do we build this? It's not that hard to build out of an SR latch. So here's our data latch. Right, it's got data coming in and set. And then inside it, I'm going to build this out of an SR latch. So here's my set, reset, my view out. Okay, so, when do I want to set the SR latch to 1? Like, in what situation do I want to set the memory to 1?
And set is 1.
When set is 1, okay, but not just when set is 1.
And data is 1.
And if data is 1 also, right? So if set is 0, I just want to ignore it, I don't care. If data is 0, then I don't want to remember a 1, I want to remember 0. So I can just, for the set line, I can just use an and say, look, if data is 1 and set is 1, then we're gonna say set. When do I want to reset? When do I want to actually remember a 0?
Data is 0.
When data is 0 and
set is 1.
And set is 1, right? So I can say, I'll have an and here, but then also like a not. I'm going to invert the data, and then there. I don't know if you can read that, but. So that's it. I mean, it's not actually that much on top of an SR latch. It's just like, but it gives us a little bit of convenience to not have to manually like. All right, this is just doing that little decoding and saying, all right, do we want to set or reset based on the data and based on whether we want to set at all. Questions? Yeah, Dana.
And this is what RAM uses?
Yeah,
How many of those?
a lot. How big is your RAM? I don't know.
I don't know.
Let's see. Probably in here I have about like, I don't know, 8 gigabytes. So you know, if this is 1 bit, how much is 8 gigabytes? Well, the giga means
Billion.
it's like a billion. It's not actually a billion. It's 2 to the 30th. Times another 8 because that's bytes and there's 8 bits in a byte, right? So like 2 to the 33rd of those, they're like 8 billion. Looks like that big. No big deal. Yeah, I know, right? I mean, when you, it's like somehow we all know this, but then when you're like, okay, no, there's like tiny things that like do this, and but there's 8 billion of them. You're just like, what? Now, obviously, like, you know, what does an AND gate look like? You know, on that scale, it doesn't look like a, you know, you can't see like little wires, like, it's like a little tiny patch of like silicon that's been printed in a certain way so that like electrons flow over it in the, you know, but conceptually, that's what it is. So let's see. Okay, good. Because yeah, I think I have one more opportunity to blow your minds before our class ends. So, because there's one other very important thing that is still missing, which is like how do we know, how do we decide when we want to do this? Because like, you know, like maybe I tell the ALU to compute something, and so like, you know, the electrons are flowing through the ALU and they're getting there. How do I know when, you know, the data has arrived and like the electrons that I want are here so that I can say, you know, to set it? Because like, you know, different electrons are going to, well no, like different signals are going to take different amounts of time to get through the circuit. And so you can imagine weird things happen if you're like, okay, yeah, set it now, but like at that time, like this signal did make it, but this signal hasn't made it yet, and you're like getting weird inconsistent things, right? So we need some way to synchronize things so that even though different signals take different amounts of time to get through the circuit, we have some point where like, okay, everything should be okay now. Now we're gonna all like, you know, save the memory all at the same time, or we're gonna, this is when we know for sure that everything's arrived, so now we can safely read and like move on to the next thing we're gonna do. And so, Because otherwise, right, you would be reduced to basically like trying to make things so that every single pathway through the circuit is exactly the same length. So that everything takes exactly the same amount of time to get there. And that's A, extremely tedious, and B, probably not even possible. Because like physically, you just can't do that, right? So we need some way to say, okay, this signal came really fast, we're still waiting for this signal, but we know that everything is going to take at most this amount of time, and then we can, okay, so this is what a clock is for. So every CPU has a clock, which is probably literally a tiny piece of quartz crystal that has some electricity flowing over it, and then like weird physics happens, and it vibrates at a certain specific frequency. I don't know how that works. It's pretty crazy, but so that is then outputting a signal. Typically, it just like goes 1 0 1 0 1 0 at a very specific rate. Okay. So then the question is like if we have a wire coming that has this clock signal that's going between 1 and 0 at a specific rate, how do we use that to kind of make sure that things get synced up properly? So. I'll tell you the simple version that makes sense. There's a more complicated version that I think you actually need, and I don't quite understand why, so maybe I'll leave that out for now. But here's something simple you could do, right? So here we've got, this is the clock line coming in. This is our set. Right? You could just do something as simple as this. So here's an AND. Right, this is an AND gate. So this is like whether we want to set, and there's an AND here that's just like, look, we're not actually going to set anything until the clock turns into a 1, right? When the clock is 1, now like anything that's coming in, we're like actually saving to memory. But then when the clock goes back to 0, it kind of like shuts everything off, and we're not actually storing anything to memory. We're like, that's the time when we're waiting for signals to propagate from memory. Now, I think this is actually not quite enough, and this is the part that I'm not sure I understand well enough to explain it, but typically I think you actually have like 2 of these in sequence, and they kind of like, so like when the clock goes to 1, it loads it in here, and then when the clock goes to 0, it cuts this off, and then it activates the second one, and it copies the value from here into the second one, and then we can read values out of the second one. That's the part I thought about this a lot yesterday, and I couldn't. Well, okay, full disclosure, I thought I understood it, and then I decided I would try explaining it to my 10-year-old, and I said that part, and he's like, "Why?" And I was like, I don't know. So, anyway, if I figure it out, I'll tell you. But, but the point is, right, that we've got this clock that's going back and forth really fast. Okay, and when you talk about like, we say, oh, how fast is your CPU? Oh, it's 4 gigahertz or whatever. Like that's what you're talking about. You're talking about how fast does the clock go back and forth, every second. So. Like 4 gigahertz, right? That's 4 billion cycles per second. So, like that's how fast a computer can, compute something and store it into memory, and then do it again. Like maybe 4 billion times every second, you could store something in the memory, read out a value in memory, right? And that's also how that has to be. You have to be able to get through the whole ALU and everything, like to read something from memory, take that into the ALU, do an operation, and then take that output and store it back into memory. That all has to happen in one cycle, right? Or else, like, if things don't get there in time, you're going to miss them. Because, like, they have to finish computing, and the electrons have to get there before the next clock cycle hits, so that they can be, stored in the right place. So again, this is also mind-blowing, right? That again, we know computers are fast, right? But literally 4 billion times per second, you can read something from memory, go through the ALU, do an operation, store it back in memory. I don't know, that's crazy to me, but anyway. This is also, see if I have time to say this. for like 1 minute. If you've heard about overclocking, right, what's up with that? So, right, there's like a certain amount of time that signals would take to get through the whole circuit, and the clock cycle has to be slower than that to give things time to get there, right? So when you manufacture a CPU, you engineer it so that there's a healthy margin of safety, right? So it's like, okay, actually the signals take this long to get through, and we made the clock cycle like 20% longer than that just to make sure, right? But if you want to squeeze that 20% extra performance out of it, you can just run your clock a little bit faster, and as long as all the signals get through that fast, you're okay. But if it gets too fast, right, you start losing things because signals don't quite make it before the next clock cycle, and that's when you start getting like weird glitches and stuff. But anyway, it also generates more heat, of course. But that's what overclocking is. All right, cool. I will see you all on Thursday.